Hi, welcome back to day 4. I've decided to break day 4 up into two parts. So this one's called 4a. We will take a look at just summarizing some of the techniques that are used for solving limits or taking limits. And then in 4b, start talking about the slopes of tangent lines, which will lead us into the actual calculus. All right, so for starters, let's look at the limit. Oops, I don't need red here. The limit as x goes to 0 of sine x over 2x squared minus x. You can see that if I just did it by substitution, the bottom turns 0, so we can't do that. So the next thing to do maybe is to factor this and see if something nice happens. So we could factor an x out of that, and that would give us 2x minus 1. And then using the properties of limits, split this into two limits. Namely, the limit is 0 as x goes to 0 of sine x over x times the limit as x goes to 0 of 1 over 2x minus 1. Right? Because sine x over x times 2x minus 1 can be written down as the product of two functions. And so the limit of the product of two functions is the product of the two limits. We've seen in the previous videos that the limit of sine x over x as x goes to 0 is just 1. And this one, as x goes to 0, I can actually make the substitution, so this becomes 1 over negative 1. So we're multiplying those two. And so the answer is negative 1. Now, what we're going to do over the next 8 examples is some of them are very straightforward, some that require factoring, some that require some other ingenious ways of taking the limit. And what I'll do on the right-hand side is to summarize the strategy that's being used to actually evaluate the limit. In this first one, I can just substitute the number in. So we'll just say sub in. And so this simply becomes 2 times 2 squared minus 3 times 2 minus 1. And that would be 4, 8 minus 6, 2 minus 1, which is 1. In the second example, if I put negative 2 in there, i.e. substituted, always check and see if it works or not. And so this would become 2 times negative 2 squared minus negative 2 plus 1 all over 3 times negative 2 squared minus 2 minus 5. And you can see at the bottom here, this will be 4 times 3 is 12 minus 7, so that's 5. And so since the denominator is defined and not 0, we can proceed. And so the top turns out to be 8 plus 2 is 10 plus 1 is 11. And so the answer is 8/11. And so this was also just done by subbing in the value. Now, with this one, if we do, can we do this by subbing in? Well, let's see. If I put 4 in there, I'll get 4 minus 2 on the bottom, which is 2. On the top, I'll get 16 minus 4, which is 12. And 12 divided by 2 would be 6. And so that's just the root of 6. So that one worked. Now, in case you wondered whether one should have factored this, and then because x minus 2 is a factor, and it would cancel that x minus 2, that would work. It would still work, but it's just not necessary because substituting works. So I end up getting 16 minus 4 divided by 4 minus 2, which is the square root of 12 over 2, which is the square root of 6. So while factoring would have worked, it wasn't necessary for this one. So subbing in again worked just fine. This next example, I can't just sub this in, because if I put 2 in, the denominator becomes 0. And so in a case like this, always see if you can factor the numerator to see if it'll help get rid of this denominator. And the top happens to factor into x minus 2 times 2x plus 1 all over x minus 2. Just going to double check that this works. 2x squared minus 4x plus 1x, negative 3x minus 2. Yeah, that worked. And so these two factors cancel. And so now I can actually take the limit as x goes to 2 of 2x plus 1. And this would be 5. So this was done by factoring. That was the strategy. Keep in mind that when we say the limit as x approaches 2 is equal to 5, that's true, even though this function is undefined at x equal to 2. You'll recall that limits simply mean what does the y value approach, even though the f of 2 does not exist in the original equation. So this would be an example of a discontinuous function that has a hole at x equal to 2, which we saw in previous lessons. All right, let's move on. Number 5. Now, again, we always try substitution first, and if I substitute x equal to 3 in here, that's not going to work. And so this technique, and anytime you see radicals like this, see if you can multiply the offending piece, which is the bottom here in this case, by its conjugate. Now, oh sorry, not the bottom, the conjugate of the bottom, the conjugate of the top, and hope that something nice happens. So the conjugate of the top would be x plus 1 plus 2, all over the root of x plus 1 plus 2. And this becomes, so I'm sure you've learned in your earlier years about rationalizing denominators. In this case, we're rationalizing the numerator. The top looks like a minus b times a plus b, so that just ends up being a squared, which would be x plus 1, minus b squared, which would be 4, all over the root of x minus 3, times the root of x plus 1 plus 2. The top turns into x minus 3 all over the root of x minus 3 times this conjugate value that we wrote earlier. And this becomes the limit as x goes to 3. Now, x minus 3 on the top divided by the square root of x minus 3 would be the square root of x minus 3. And we've got that divided by the root of x plus 1 plus 2. And now we can substitute the 3 in. Now, the top turns to 0. I guess the bottom doesn't really matter so long as it's not 0. This ends up being the root of 4, which is 2 plus 2, which is 4. And so this ends up being 0 after all that effort. So this one was done by using conjugates. Conjugate. Okay, and we rationalize the numerator in this case. Now, this next question, it looks like a difference of cubes. I know it doesn't quite look like that to you, but we could do that. Let's see. Now you're wondering why I said this is could be written as a difference of cubes. We're going to do this by using a technique called variable substitution. Variable substitution. All right. the way this works is we're going to let u, or any variable you like, equal the messy part of this, which is the x plus 27 to the 1/3. And so if I were to cube both sides, I end up getting u cubed would be equal to x plus 27. And now we end up with u cubed minus 27 is equal to x. And so now I can make my substitutions. So as limit. Now, you don't want to be writing the limit as x goes to 0 here, because we're about to change the variable from x's to u's. This messy part, remember, was u, so that's u minus 3 on the top. And on the bottom, we've got x, which we said is u cubed minus 27. We could, I suppose, take the limit just using u's and then transfer it back into x's and then keep the limiting variable x going to 0. But from a point of good form, we need to change this limiting variable from x to u. So as x was approaching 0, if we take a look at that top substitution, that if x was equal to 0, if I put 0 in there, we get 27 to the 1/3, which is the cube root of 27. And so, sorry, if that should say if x was equal to 0, then u would be this cube root of 27, which is 3. So we're going to change this now to say u is approaching 3. You notice I still can't make the substitution because I'll end up getting 27 minus 27 on the bottom. However, the denominator being a difference of cubes factors. So we end up with u minus 3 on the top, u minus 3 on the bottom, and the quadratic factor would be u squared plus 3u plus 9. And now the u minus 3's cancel. And so I end up getting the limit as u goes to 3 of 1 over u squared plus 3u plus 9. And that just turns into 1 divided by 9 plus 9 plus 9, or 1/27. Okay, so that technique is known as a variable substitution. Number 7. We're going to do this by a similar technique, namely variable substitution. This time we're going to let x be equal to this x to the 1/4 at the bottom. You might want to pause the video at this point and see if you can do this one on your own using the similar technique that we just did on the previous screen. Okay, I'll give you a chance to just pause this here and then come back. All right, if you've just returned, hopefully you got it, but if you didn't, we'll proceed like this. So if x, oh sorry, I didn't mean to say x is equal to, I meant to say u is equal to x to the 1/4. And now if I were to do the 4th power on both sides, raise both sides to the 4, I end up getting u to the 4th is equal to x. And remember, we want to change our limiting variable. And so if x is going to 81, right, if x is approaching 81, from the top here, we get from this statement, u would be approaching the 4th root of 81, which is 3. And so this becomes the limit as u approaches 3 of 81 minus x, but we said x was u to the 4th, all over u minus 3. And this becomes the limit as u goes to 3. And the top being a difference of fourths, because 81 is 3 to the 4th. Just like a difference of squares factors, so does a difference of fourths. So it factors into 3 minus u and 3 plus u. That would be the 9 squared minus u squared. And the other factor would be 9 minus u squared. And the other factor would be 9 plus u squared. Or 9 plus u squared all over u minus 3. Now hopefully you can see how we can cancel the 3 minus u and the u minus 3. They really just differ by a factor of a negative. So I could put a negative here and then change this to a negative and a positive. In other words, I multiply the top and bottom by -1. And now these things can cancel because they both say the same thing. So we end up getting the limit as u approaches 3. Don't forget that negative sign of 3 plus u times 9 plus u squared. And if we substitute u equal to 3 in there, we end up getting -6 times 3 squared is 9 plus 9 is 18. And so that ends up being -108. Okay. Another variable substitution question. Okay, just one more to go. And that is absolute x. The absolute value function always poses problems because you don't know how to actually break this down. But just remember what the definition of absolute x is. Absolute x is equal to x if x is greater than or equal to 0. And it's equal to -x if x is less than 0. And so we can look at two cases then. So case 1 is that x minus 2 is greater than 0. And the other case, case 2, is that x minus 2 is less than 0. Now, if x minus 2 is greater than 0, then the absolute value signs don't do anything. And so this limit ends up being the limit as x goes to 2 of x minus 2 divided by x minus 2. And in this case, the second case, if x minus 2 is less than 0, then this limit becomes the limit as x approaches 2. And you notice here it said the absolute value of x is negative of x if x is less than 0. So we're saying if it was less than 0, then this just becomes negative x minus 2 over x minus 2. And this cancels there, this cancels that. And this limit ends up being 1, whereas this limit ends up being -1. And you'll recall that if you do this and the two limits are not the same as x approaches some value, then the limit doesn't exist. So the limit does not exist. You might wonder, what does this mean in this case? Like, why did that not exist? Well, if you were to take a look at the graph of this function, it looks something like this. This is 2. And if you were to graph that function, absolute value of x minus 2 over x minus 2, this is what it looks like. And so you can see that as we're approaching 2 from the left-hand side, the limit is 1. But if we're approaching 2 from the right-hand side, sorry, from the left-hand side, the first one from the right-hand side, this one's -1. And so this is what this function looks like. And so as the function is approaching 2, the two one-sided limits are different. And that's what we saw when we did the algebra there. Okay, so that's why the limit doesn't exist. Well, I guess that takes care of that. Thank you very much for watching Day 4a. And in the next one, we'll be getting into the actual calculus and introduce Newton and Leibniz. Take care. Bye.